Good day and welcome back to part 4 of our discussion on the chain rule. In this video we will kind of continue on our exploration by looking at a few more common examples. So the first example is related to tangent lines. And we can ask these questions in a variety of different ways. For this example, what we would like to do is determine the points on the graph of a function at which the tangent line is horizontal. So let me kind of just quickly emphasize a few key things. First of all, we have to make sure that our final answer matches up with whatever the question is asking. Here it's telling us to find the points on the graph. So that would be an ordered pair that lies on the graph of this function f of x. So I'm going to circle that just to make sure at the end of the problem we present our answer in the correct form. And we want to know where that tangent line is horizontal. So note the slope of the tangent line at a point is the derivative, and a horizontal line has a slope of 0. So this is just a fancy way of asking us to solve what are the values of x where f prime of x is equal to 0. So that's what we need to do. So we have our function 2 sine x plus sine squared x. And I'm going to go ahead and write that as sine of x quantity squared so that the differentiation rule we apply is going to hopefully be as clear as possible. So differentiating term by term, we would get 2 cosine x. And when it comes to differentiating sine quantity squared, we use the chain rule. The chain rule tells us we differentiate that outside function. 2 comes down front, the new power is 1 less. We substitute in the inside function, and then we multiply by its derivative. And what I want to know is, can we solve for the values of x where this derivative is equal to 0? So we're solving for the x value that satisfies this equation. Now, note we can approach this from a very algebraic perspective. You have 2 terms, and they each involve a cosine. In fact, they each involve a 2 cosine. So let's go ahead and factor that out. So if we pull the 2 cosine out of each term, we're left with a 1 in the first term and a sine of x in the second term. And recall, the only way a product of 2 things can be 0 is if one or the other of the 2 things is 0. That is to say, cosine of x is 0, or 1 plus sine x is equal to 0, which means sine of x is minus 1. So we need to decide what are the values of x, and note there's no restrictions whatsoever. So by the periodicity, there's going to be a whole bunch of solutions where cosine is 0 and sine is minus 1. And just to aid us a bit, let me draw the unit circle. Remember that any point on the unit circle, and just picking a random point, if you form the angle theta going from the positive x-axis up to that point in the counterclockwise direction, the coordinates of the point will be cosine theta, sine theta. So if you want to know where is sine equal to minus 1, that would occur precisely at 3 pi over 2. And if you want to know where cosine is equal to 0, we can note that cosine is the x-coordinate of a point on the unit circle, and the x-coordinate of a point on the unit circle is going to be 0 only if you're at pi over 2 or 3 pi over 2. So there's a bit of overlap there, which is perfectly fine. So let's just kind of summarize this. Cosine x equals 0, that means x is equal to pi over 2, 3 pi over 2, but note there's a whole bunch of possibilities. Every time you go an additional 2 pi, you end up with the same value. So in our case, we can even simplify that a bit and say if you're at pi over 2 and you go any multiple of pi, you're going to end up at 3 pi over 2 or back at pi over 2. So we could write this as pi over 2 plus n pi, and this is where n is any whole number. Sine x is equal to minus 1 only when x is equal to 3 pi over 2, or any 2 pi multiple that we add on to that. So for both of these, note n is a whole number. But we don't have to worry about this 3 pi over 2 plus 2 pi n, because note that's included over to the left. So we would just be repeating our previous point. If you did, that wouldn't be an issue, but I'm going to leave that out just to make my solution as simple as possible. So our points of interest are as follows. So we would want to know when we substitute in pi over 2 plus n pi, what do we get back out of our function? And it turns out it depends. And what it depends upon is whether this n value is odd or even. So let me go ahead and just do some computations to the side. And note, this is not an easy problem in the sense that there's a whole bunch involved, but all of the ideas are really good ones, which makes it a good example for us to work through together. So if I want to know what is f of pi over 2 plus n pi, I can go ahead and substitute that in to our function f, giving us 2 sine of pi over 2 plus n pi plus sine of pi over 2 plus 2n pi squared. And this is a point where it matters whether n is odd or even. So note, if n happens to be 1, then you're at 3 pi over 2, where sine is equal to minus 1. But if n happens to be, say, 0 or 2, you're at pi over 2, or if you go 2 pi around, you're back at pi over 2. So the value of sine there would be 1. And in the second piece, it doesn't really matter what it is because it's plus or minus 1 and we're just squaring it. So let's just kind of note, if n is even, then this is going to be equal to 2 sine of pi over 2, just by the period of sine, plus sine of pi over 2 quantity squared, which equals 2 plus 1, which is 3. But let me note, similarly though, here if n is odd, then f of pi over 2 plus n pi, this pi over 2 plus n pi when n is odd, is going to give us the 3 pi over 2 case. So I know it's not an easy problem because there's a lot going on, but 2 sine of 3 pi over 2 plus sine of 3 pi over 2 squared. So this would be 2 times minus 1 plus minus 1 squared, which is a negative 1, because we have minus 2 plus 1. So for these points, I'm going to actually simplify this and write out what happens in either case. So when n is even, your point would be pi over 2 plus n pi, comma 3. And when n is odd, your point would be pi over 2 plus n pi, comma minus 1. Now note, it would have been a much simpler question if we restricted everything to being between 0 and 2 pi for our inputs. But I did not do that because working with trig functions in general is something we will do throughout the course. So it's never a bad idea to walk through and understand an involved example such as the one here. And I always do like to remind us that when it comes to mathematics, there will be many difficult problems we encounter that we don't quite understand or see at first glance or first attempt or first session, but sometimes you have to let these things settle for a bit, come back to it after you've thought about it for a while. Let's move on to one very different example. So another kind of common problem is we can give you some information and ask you to determine some value. So for the function big F of the square root of f of x, can we find f prime, little f prime of 3? And the difficulty of this problem, I think for most students, is that it's very general or abstract. We're not giving you a concrete function big F, but we're giving you kind of a table of values related to that function. And just to make sure we understand what these values are telling us, this 3 that we see would tell us that f prime of 2 is equal to 3. So the 2 and the 3 along that top row would be the inputs into f in the middle row that give us the outputs 1 and 4, and the inputs into f prime in the bottom row that gives us the outputs 3 and 2. So what we need to do is calculate the derivative of little f and see if we can evaluate it at 3. And in order to differentiate this, we're going to do it step by step with the chain rule. Derivative of the outside, evaluated at the inside, multiplied by the derivative of the inside. And you guessed it, it's a double chain rule problem because we have a composition of a composition. Big F is inside the square root, which is inside big F. So continuing on, we have f prime of the square root of f of x. And now when we differentiate using the chain rule, we differentiate the outside function, 1 over 2 square roots. We evaluate at the inside function, and then we multiply by its derivative. And we are now at that ideal position to simply substitute in the value 3. That is f prime of 3, working from left to right, is f prime of the square root of f of 3 times 1 over 2 square roots of f of 3 times f prime of 3. And we should be able to find all of these values in the right column of our table. So note, in particular, this 4 is telling us f of 3 is 4, and the 2 is telling us that f prime of 3 is 2. So substituting in these values, we have f prime of the square root of 4 times 1 over 2 square roots of 4 times f prime of 3, which is 2. So we have f prime of 2 times 1/2. And as we indicated earlier, f prime of 2 is the number 3. So this ends up being 3 times 1/2, which is 3/2. So this question is really getting at the idea of, do we understand how to apply the chain rule without having to worry too much about any, I'll say, complicated or overly difficult differentiations. And that finishes the examples for this current video, but we're going to finish up this topic of the chain rule with another worksheet. So once again, you can notice we're getting a lot of practice in with these ideas and concepts so that when we really need them later on in the course, they will be quick and efficient as we've claimed. You can find a chain rule worksheet in Canvas. As usual, I recommend give yourself 20-25 minutes, however much time it takes, to go through and begin working on these examples. You can find full solutions written out on Canvas, and in the next and final video dealing with the chain rule, we'll go over 2 of these examples together. So stay tuned and take care.